Give you some more time to work with that sucker. 2-4, of course, is everybody's favorite so far, the epsilon delta stuff. Yeah. Okay. So anything from more recent homework stuff that we've done? We've made it 2, 3, 2, 4, 2, 5. There's a few things I want to go back and tighten up. Other than that, we basically finished those. There's one big theorem in section 2.5 we have yet to discuss. I think I assigned the monk problem. I don't know if anybody made it that far. I love it. There's one of my favorite problems, and that should immediately make you anxious. There it is. There's number 73. A Tibetan monk leaves the monastery at 7 a.m. and it goes from there. I can't remember if I'm almost certain I assigned that. You'll see when you get there. So it involves, that problem involves the theorem that we're going to talk about from that section. This Tibetan monk climbing a mountain. Okay, all right. So no questions from homework stuff nothing. Okay. How you guys doing all right? What's going on? You guys all right? Yeah? Is it just early? You gotta start looking into caffeine. I don't know. If you've never drank caffeine, just don't start now. But if you have, just keep freaking going. Do it. Yes?
So I have a question on 2.1.
Yes.
So problem number 8, and then sub problem A, sub problem 2. Yeah.
I got you. I know, it's sort of like reading a legal document, right?
Yeah.
Subsection 2, paragraph 8. That is basically the exact same problem I put on the quiz, right? Number 2?
Yeah.
Yeah. So 8 in section 2.1 gives you this formula for the displacement. It gives you this displacement formula. Pick the book up, Jeff. There you go, buddy. So there is the displacement of a particle. T is in seconds. S should be in meters, maybe. Centimeters. I like it. So this is centimeters, and this is seconds. Blah blah blah. Find the average velocity. Okay. So find the average velocity. Your specific question was on this one. Average velocity for this time period. Let me ask you a little side question. First thing is, average velocity is another name for what in this problem? Slope. I love it. If I told you that t is 7 and s of t is 10, t is 8, s of t is 21, can you figure out the slope? How would you do it? Yeah, 21 minus 10 over 8 minus 7. Easy shit. So what do I know here? I know t is 1 and t is 1.1. What am I missing? To be able to do that easy, what am I missing?
Y.
The y, the s of t for each situation. So I need to know what s of 1 is and s of 1.1. If I can make 2 points, it's freaking algebra after that. Every problem basically in 2.1 is an algebra problem. It's just trying to transition you from what you know in algebra to what we're going to do in calculus. What we do, of course, is a lot more powerful than algebra, which is why it's a little more complicated. But this isn't complicated. This is just make the points, get the slope, next. Is that decent? I like it. So now you would just plug a 1 in, plug a 1.1 in, get the values, do it just like you did here, kick ass. That's all of 2.1, basically. The last problem is a little extra because it's a crazy ass function, so it asks you a few more questions. But they're basically all this. Anything else from homework? I mean, yes?
The same question. I think I'm looking at number 8, it says to estimate the velocity. The answer would be the one off of 1.01, correct?
No. So 1, 2, 3, 4 gets what are 1, 2, 3, 4 doing? It goes 1, 2 for part 1, 1.1, and then 1.01 probably, and 1.001,
0.001.
and then 1.001.
I meant the last one.
I know. So that's not the answer though.
No?
It isn't. You're going to develop a pattern, and then you're going to continue to and see where the pattern seems to be going. Because would you stop here if you want to get more precise? What would you do? 1.0001, 1.00001, right? But it didn't. The problem didn't ask for that. You could, if you wanted to, go a little further and say, Jeff, this problem is stupid. I'm going to go a little bit closer. I would have no problem with that, really. But basically, it's just asking from what you see, what's the pattern? Where does it seem to be going? It will definitely not be what you get here. So if I saw, I'm not saying this is it. If I saw 8, 7.1, 7.023, look at me writing that, 004, you don't say that's the answer. What does it look like it's approaching?
7.
Freaking 7. I love it. Does that make sense? This can't be the answer, because if I took another step closer, it won't be this anymore. But I can see what it looks to be going towards. Could I be wrong? Oh shit, yeah, right? This is my guess. Calculus is going to give me the exact frickin' answer. Right now, we're using algebra to do something you can't really do with algebra. So your guess might be wrong, but it's going to be close. Or right, if you're lucky. The right answer might be 7.000279. Right? But to me, that's freaking 7. Maybe. We're doing this by hand, so of course our guess is not going to be perfect. So I call it a guess. Yes?
When it comes to showing work on these algebra-heavy problems, do you want us to like show everything? So like me
You could do this.
1.1 from that?
Yeah.
Okay. Okay.
Yeah. So, I mean, one kind of way to do this problem is, if I wanted to do this problem, you could just set up this, and then just give me the answer, to be honest.
Oh, okay.
Yeah.
All right.
Because the rest of it's just plug in the calculator, right? So sometimes when I say show work, I just want you to set up for me the idea you're using and then plug it in the calculator. I don't need to see 8.7 minus 8.1 is 0.6. No, I don't need to see that shit, right? Okay.
Got it.
When I say show work, very often it means show me the setup of the idea. Yeah, okay. Don't just give me a number. I'm like, where'd that come from? Solutions manual, no good. All right, anything else from homework stuff? I got all excited because I got some questions. I live off of freaking questions. Right? I live off of questions. If I don't get them, I go a little crazy. Because that means that I know you have questions, and you're just not asking it for some reason. It drives me crazy. Okay. So let's do a couple things from the homework that I haven't really explicitly said in class. This is something we've used already, this idea. 2.3 sets up all these limit laws. And they make it all sound so formal and complicated. So for example, one limit law is the limit as x goes to a of f of x plus g of x equals the limit as x goes to a of f of x plus the limit x goes to a of g of x. We've already used this idea. Totally. Right, so for example, what's the limit as x goes to 1 of x squared minus x? You're all overthinking it. What do you get when you plug a 1 in?
0.
Okay. And what's true about this function? Is it a nice function? Yeah. When I say nice, we now have a little more better way to say that. Is it continuous? Polynomial is continuous. That's beautiful. So it's going to go through all of the points that it looks like it's going to go through. That's why I'm allowed to just plug 1 in. So I'm using this law with a minus instead of a plus, but still, that's 0. So you're going to have a law that has a minus here. You're going to have a law that has a times here. You're going to have a law that has a division here. The division one, of course, this limit can't be 0, because you can't divide by 0, but otherwise it holds. Okay, like, in fact, you did that division law in pre-calculus already when you found rational functions, horizontal asymptotes. You did the limit of the top divided by the limit of the bottom. You did that already. We'll do more of that today, actually. We're going to remember what we learned from pre-calculus. All right, so that's one little thing. In section 2.3, they have these limit rules. Here's a really useful one that we've already used. What do you think this is?
What do you mean?
What's the answer?
Square root of 11.
Yeah, yep, square root of 11. So if the function is continuous, I'm allowed to take this inside. So basically what we just did was we did this. Put the limit inside. If the function is continuous, and now we know that what kind of things are continuous? Radical functions, rational functions, all on their domain, right? I like it. Maybe. Okay. And here's the funky thing from section 2.3. I love this theorem. If you've done section 2.3 homework, hopefully you've seen this. It's called the Squeeze Theorem. This is not my name for it. It is the name for this theorem. And once you see the theorem, you'll be like, what the hell else would you call it besides freaking Squeeze Theorem? I always think about the original Terminator when I do this. So you'll see why in a second. Squeeze Theorem. Whoa, Jeff. I can't even spell theorem there. So if I have a setup where I have f of x is less than equal to g of x is less than equal to h of x for all x. All right, let me let you just absorb that for a second. What's another way to say that quicker? What's true about g?
In between.
In between, beautiful. If that is true, and the limit as x goes to a of f of x equals the limit as x goes to a of h of x. All right, now. And that equals some finite number, right? So at a, f of x, now what's the one on the top? What's the biggest function? What's the one that's
H of x.
biggest? Yeah, h of x. So on top is h of x. So at here, h of x has to approach there, right? Now, to be honest, it didn't have to exist there. Wow. So there's h of x. F of x has to do the same exact thing, but f of x is going to be the smallest one, right? They might sometimes be equal, but it's got to come here. Well, so there's f of x. Cool. Let me put it over here. This is h and f. Where's g of x?
In the middle.
Lives in the middle. And it says that sometimes it could equal these things. Maybe it's bouncing around. Woo! This is like a sign being contained in there. So what do you think this means about the limit of g of x as x goes to a? What's the limit as x goes to a of g of x? What's it gotta be? Yes, do you see why they call it the frickin' squeeze theorem? H and F, squeeze. And if you've ever seen the original Terminator, I always think about the last part where the hydraulic press comes in. Here's the Terminator is the G function. Here's the H, here's the F function. And yeah, shit. Squeeze the shit out of it. I like it. If you've never seen it, I'm sorry. Don't worry, you don't have to know it. But you see why they call it squeeze? Ceiling, floor, meets, whatever's in the middle is going to be in the same place they are and dead, right? Maybe. So how the shit do you use this? This is great for like the idea of it. How the hell do you use this thing? Okay, here's how you use it. Oh, let's see, what do you want, Jeff? Let me pull one from here. Right out of the homework. I'll do one like that. Yeah, okay. Ooh, it's even better. I like it. Yeah, let's do one like that. Sure, that'll work. X goes to 1. Yeah, let's make it 0. Okay. Which part of this function has bounds to it? This whole idea has to work with functions that are bounded somehow, right? Which part of this is bounded?
Sine function.
The sine is bounded. So let's write down what this sine of I don't give a shit has to live between what?
-1 and +1.
Yeah, bam. The inside being all freaky doesn't matter. Sine of whatever the shit has to live within -1 to 1. Now this is kind of cool. Watch what we're going to do. Is that the function that this is asking me about? So let's build it. Let's build the function. So what's the first thing that's missing there? Don't tell me x yet. What's missing? I don't have sine in the... Where is sine in the function they're asking me about? Where is it? The exponent of e. So I better freaking introduce e. So let me raise e to everything here. You see how we're getting closer to the function they're asking me about now, right? So do you see how that function is now contained? Still. And now what's the last thing that's missing? The x. So let me just introduce an x. And then, to be honest, the very last thing that's missing is the limit. So if I take the limit as x goes to 0, let me put it up here. You guys are starting to not be able to see it now there. Poor little thing. Now what's the limit as x goes to 0 of this? What is this? What is e to the -1? What kind of thing is it? It's a constant. So what happens when you let x go to 0? 0. What happens over here? 0. So whatever the hell this is in the inside gets smushed. Do you see it? Do you see this is the computational analog to the visual? That is getting smushed. What's the only option for the limit of this then? It's got to be 0, because it's got to be greater equal to 0, and it's got to be less than or equal to 0. There's only one thing that does that, 0. All the options it could have been got smushed down to 1. So the answer is blah, blah, blah equals 0. Bam. So what do you do when you have a squeeze theorem problem? You find the part of the problem that naturally has bounds. Write it down. Build in all the other shit. As you build it, those bounds will still be there. And then you apply your limit. Maybe. That's kind of a funky-ass little thing. There's not that many problems in the homework. It's not that big of a deal, but it still is useful. It's parts of later theorems. They build off of this. Okay. Yes?
Could you do one more example?
Sure. Let me see. So we got all this here? Okay. Oh, let's see. What else can I throw at you? Sure. Let's do... Yeah, I guess I can still do that. That's fine. Yeah, I like it. Let's do that. No, let's just keep it like this. All right. Doesn't really matter. Let's see. Sure, I like it. Why not? I can't throw too many different looks at you. So, which part has a bound? Sign. So what's true about sign? It's got to be between. Yeah.
Maybe 1, 1.
Yep. Well, this is a little bit easier because now I just have to. What's the only thing I'm missing now? X cubed. So if I multiply everything by x cubed, yeah. Then you take limits, you get 0, 0, right? You try to come up with a, is that cool? It's exactly the same idea. What's a more interesting problem, Jeff? I don't know, Jeff. Yeah, okay. What about, this is a good one because you need to remember this anyway. What about the limit as x goes to pi, x minus pi times inverse tangent of, what is it, John? What about inverse tangent of natural log of x squared plus 3.7? Doesn't that look yummy? Who remembers a damn thing about inverse tangent? What's it look like? I love you guys. What does tangent look like? What does tangent look like? No, what's it look like when I graph this? We did this before. Where are the asymptotes? Where are the main asymptotes?
Is it a negative pi over 2?
Yeah, because tangent has cosine on the bottom, so it's going to be undefined when cosine 0 at the pi over 2 shit, right? I don't know if you guys remember this. Why does it seem like tangent should not have an inverse? Because is this the end of the tangent graph? No, because it just repeats forever in both directions, blah, blah, blah. And what test does it fail to try to have an inverse? Horizontal line test, right? Why horizontal? Vertical tells you it's a function. If I flip the function, I get the inverse. So instead of flipping the stupid function, I flip the test. Horizontal line test is a vertical line test flipped. So if it passes the horizontal line test, it has an inverse. It doesn't, unless I say, oh, I just want it between negative pi over 2, and then that's what we do. That's why when you do inverse sine, inverse cosine, inverse tangent, you might get a reference angle, not the angle you want. Does that sound at all familiar? No? All right, oh shit. That's why, because I had to restrict the domain in order to have an inverse exist, right? Remember, how about sine? How do I have an inverse exist for sine? It looks like this shit, right? Does that pass the horizontal line test? No, unless I cut it to there, right? Negative pi over 2 to pi over 2. Hey, holy shit. Cosine would be 0 to pi. Which is why the stupid law of sines sometimes had two possibilities. I don't know if you guys remember that. It was like the SSA, so I always call it the ass one because it's the ass that, it's an asshole because it could have two different possibilities. Sorry, if that doesn't sound at all familiar. Oh, shit. All right. Do you have to know any of that for this? No. So inverse tangent would be this, just flip. So inverse tangent looks like this. So what's it live between? Flip everything. So now this is there, this is there. So what's it live between?
Same.
Negative pi over 2 to pi over 2. Big ass. All right, so how can what part of this is bounded? Yes?
So sorry, when you flip that, it looked like the domain was all real and the range was pi over 2.
Of course.
Is that what you're
Totally.
saying? Okay.
What's the range of tangent? Even after I restrict its domain, what's the range of tangent?
All real numbers?
And what does an inverse do? switches the x and y. So what does an inverse do? Switches the domain and range. Domain of this one is negative pi over 2 to pi over 2. So the range of the inverse is going to be negative pi over 2 to pi over 2.
Gotcha.
The range is infinite. Very good to realize. That's all inverse functions do, right? Switch the x and y. That's all they do. But what are the x's? Domain. What is the range? Y is the range. So it also switches the domain and the range. That kicks so much ass to realize that. So what part of, get out here. You're not the one I'm looking at. What part of this is bounded then? What part of this do I not give a shit about? And some of you guys are like, whole damn thing. I'm not going to do that. You're probably not going to notice I didn't do it. Meh. I don't give a shit about this shit. Because what's inverse tangent, no matter what's in here, it's got to be between negative pi over 2 to pi over 2. So I can say negative pi over 2 less than or equal to this business. Less than or equal to pi over 2. Then I bring in what I'm missing. So multiply by x minus pi. Then when I take limits, what's the limit as x goes to pi of this? If I let x go to pi, this goes to 0. If I let x go to pi, this goes to 0. So in the inside, this thing is going to go to 0. You'll notice that 0 very often is the answer. But don't just put 0 and go, it's always the answer, Jeff. No. Okay. So there's a theorem from section 2.5 that we didn't cover yet. This one's really kind of nifty. Once you see it, you should kind of, not you all shipwrecks, but once you see it, you should kind of go, okay, that's duh, that's simple. I'm not saying that you're condescending or anything, but you'll see, right? But it's such a fundamental idea that other theorems build off of. So it's called the intermediate, yeah, you're just right, Jeff, value theorem. Heretofore known affectionately as the IVT. You're not working too good. Let's try you, Blue. Come here. So here's the idea of this. If I have a continuous function, f continuous, at least on some interval a to b. So I'm talking about some interval a to b. So it's continuous on that interval, and f of a does not equal f of b. So let me just put, let's say here's f of a, and here's f of b. How's that? Kabam, kabam. All right, Jeff, you're all cross-eyed. Setup so far so good, right? It's continuous, which means it can't teleport or do all that kind of weird shit. Can't jump. And there's some n between those. Here's n. What do you think about the output of n? Is it possible for the function to not have an output of n? That's really the fundamental question here. Is there a way for this function to not go through this line, is what I'm really asking. Is there a way? No, the only way it could do that, it's got to connect with this, doesn't it? And it's continuous, so it can't go, haha. So it's like, oh shit, I did it. Damn, there's the point where it has an output of n. So what this says is, if there's a function that's continuous here, and n is between f of a and f of b, bam, then there exists, by the way, I might put a backwards e. That's a symbol that means there exists. It's basically shorthand. So if I do that without thinking about it, when I see this, I read there exists. Then there exists c in a to b, where f of c equals n. All right, see, when I write it like that, it's like, holy shit. But parse it out. It's exactly what we just did. What's this then? What's this?
C.
That's c. since it's continuous, so are you guys at the point, anybody at the point where like, well, duh, it's got to connect, so there's got to be, it's going to take on every value between here, right? So of course there's one value. For any value between, there's going to be something that goes to it. There's no way for it to escape. So on one level, it's kind of like, good job, math people, right? But again, if we don't state this as a theorem, I can't use it to prove other theorems. I like it. And somehow this relates to a Tibetan monk climbing a mountain. So we'll see if you get that problem. Yes?
Where does it say there exists a what?
A C
Oh. Oh.
in A to B. Yeah, I like it. I like it. I like it. So that's not that bad of a theorem yet. The theorem that builds off of this is going to be a little more interesting, but that's coming up later. Called mean value theorem. Let's see, what else was there in there? Oh, yeah, all right. One of the immediate uses for this. What has to happen for there to be... so if I have a function, it's just having a good old time. What has to happen for there to be a root? Let's say that this is A. What has to happen for there to be a root past A somewhere? For there to be, what does a root mean? Where's the ground in this picture? Where's the ground? Right here, yeah. So what's a root mean? Where do roots start? At the ground. So roots are another way to say x-intercept. You guys have heard of roots, right? You have to find roots. Remember Descartes' theorem and all that kind of shit, and finding rational roots? Does that sound familiar? Synthetic division shit? No? Okay, anyway, that's what a root is, an x-intercept. How would I know there's an x-intercept besides just seeing it happen? If I kind of lost this? Let me see if I can explain. If I kind of lost, somebody erased this, where would the function be? It's continuous. If there was a root somewhere between A and B. Where should it be after B to be complete evidence there's a root in there? I love you guys. I know this is a weird question. It'd have to be down here. It'd have to be negative, right? If it's positive here and negative over there, what's got to be true in the middle? It's got to go through somewhere. It's continuous. It can't just go teleport. No, it's got to somewhere. It's got to go through. Isn't that this? Isn't that this? Stated a little more practically. So, for example, extreme concrete example. Let's see, I put an example. Where'd it go? Here. So if I have this function, where'd it go? There it is. So there's a root in 1 to 2. The same one. Might be. Yeah. So what do you guys think you should do? What's true about f of A on this picture? It is positive. What's true about f of B in this picture? Negative. So therefore there must be at least one root. What could this function do so there's more roots? They could just go to 10. Right? And then there's like 11 roots or whatever. You guys with me? No idea what sound it's making as it does that. That's what I think it makes. So how would I do that less visually, more just computationally? All I got to do is
plug in something.
Plug in, not something.
1.
Plug in 1 and plug in 2 and see if they change signs. That's it. If one is negative and the other is positive, there's got to be at least one root between there. So that's an immediate use of intermediate value theorem. How are we doing? Is that all right? No? Because if f of 1 is positive, well, let's see. What do you get when you plug a 1 in? 4 minus 6 is negative 2, negative 4, you get negative. So f of 1 is negative 1, I think, or whatever it was. It's negative. F of 2 will be 32 minus 24 is 8, plus 16 is 24. It's positive. It's way the shit up here. So what's got to happen at least once in between? It's got to cross at least once, because it's got to get up there. So it's got to go through. It's got to have an x-intercept, what I used to call doors. when I taught this. You can't go through this unless that's a door. And that's what an x-intercept is a door through the x-axis. Yes?
Will it ever happen when it's passing a root, the value is equal undefined?
Oh, if you're unlucky on what you're testing, you could have funky shit happening on either one of these. In fact, think about it.
I think my other question is, one, if the value at y equals 0 is undefined, then that means we don't have a root, even though it's passing by there.
But then, would the function be continuous?
No.
So any counterexample you can come up with requires the function to be discontinuous. Wouldn't an open circle be discontinuous?
Yes.
That's a removable discontinuity. Not a good example, because this requires the function to be continuous.
Okay.
So everything you can imagine to escape the results requires the function to be discontinuous somehow. Now, is this perfect? Well, if I put f of a in and is positive and f of b in and is positive, is that proof there is no root between them? Of course not, because it could do, wah, you know. So the inverse is not true. You got to be careful, right? So if the signs are different, there must be at least one root. But that doesn't mean if the signs are not different, there's no roots. That doesn't follow. It doesn't make sense. Okay. Okay. Then there's, oh, good, perfect. So now we get into section 2.6. Let's see if you guys remember some of this from pre-calculus.
I have a question.
Yes.
So is this basically just skipping, you don't have to find the zeros? Because can you just find the zeros to see?
Yeah, I mean, you could plug in the calculator and tell it finds it. That's
This
not
is
the
just
point.
the
This is
more-
more theoretical. Is there even a purpose to doing anything to find a root? You know, or not so much that, but is there evidence that there's a root between these two things? Yeah, I like it. So if you do get both of these come out the same sign, that's not evidence for, but it's also not evidence against. Then I don't know. Then I got to go do some other shit, right? But if it comes out to be like that, then I know for sure there's at least one root in the middle. I like it. And again, very often these theorems are kind of building block theorems. There are theorems that will use the results of this. So this is really just a building block theorem. Okay. And it's not that horrible. It really isn't. So let me ask you 3 questions. What is your name? No. Find the horizontal asymptote for these 3 situations. Does anyone, there were 3 situations for horizontal asymptotes. These are the 3 situations. Anybody remember how the shit to do that? What does horizontal asymptote mean? Let's put it in terms of the symbols we know now. Some of your pre-calc teachers showed you limit symbols, but so really, what's a horizontal asymptote mean?
Approaches a y.
As what?
As
So when you say approaches, can you show me in the air? Approaches. So what's x doing? Going to
going up or going to the right, so going positive.
approaching infinity. So what's the limit as x goes to infinity of this? So let me show you the long ass way, and then I'll show you the shortcut. Right? The long ass way is to divide the top and bottom by the highest power I see. Because what's true about this? This is something we should know. What's the limit as x goes to infinity of 1 over x? What happens to that 1 over x when I make the bottom bigger and bigger and bigger.
Smaller, smaller, smaller.
So the limit will be,
Negative infinity.
no,
That's wrong.
smaller in absolute terms, right?
0?
Yes.
There we go.
This should be very familiar. You know this from pre-calculus. And it just makes sense. What does 1 over x look like? Yeah, looks like, hey, look, what's it doing? Going to 0. So as x gets really big, this goes to 0. 1 over 10, 1 over 100, 1 over 1,000, 1 over a million, 1 over a billion. That's getting small, small, crazy small. You can make it arbitrarily small, which means the limit is 0. Okay, that part should not have been groundbreaking, but maybe it was. So watch, here's the approach. This should sound hopefully familiar if you had a halfway decent pre-calc teacher. The highest power I see in here is cube. So if I divide the top and bottom by x cubed, what's the only time I'm not allowed to divide by x cubed? What number can I not divide by? What number can I not divide by? 0. Will x cubed ever be 0? Does x ever get to, no, it's going to infinity. So that's why I can divide by x cubed. It's not, we're nowhere near 0. We're up to freaking huge numbers, right? So what's this become then, now, if I do that? What's x squared divided by x cubed?
1 over x.
1 over x. What's 1 divided by x cubed? All right, kick ass. 2x cubed divided by x cubed. 2. 4 divided by x cubed. What do all these things go towards? What did we just say? What do all these pieces go towards?
0.
0. So what's this limit? 0. Why does that make sense? Just looking at it. The top power is smaller than the bottom. Won't the bottom grow faster? So if the bottom is getting larger quicker than the top, I'm dividing by bigger, bigger, bigger. I ain't keeping pace. I'm going to go to 0. So whenever the top degree is higher than the bottom, or smaller than the bottom degree, I'm going to go to 0. It's going to horizontal aspect of the x-axis. That should sound very familiar. Anybody remember the shortcut to this? What's true here? The powers on top and bottom are the same. The highest powers are the same. Anybody remember the shortcut for the horizontal asymptote? Leading coefficients. Kick ass. Why? Well, if you do this long ass shit, divided by x squared, that's the highest power I see, what do you get? Yeah, there's 0. 4x divided by x squared is 4 over x. X squared divided by x squared is 1. 6x squared divided by x squared is 6. And 7 divided by x squared is 7 divided by x squared. These go to 0. Negative 1 over 6, which is the ratio of the leading coefficients. The leading coefficient thing was a shortcut. And then finally, this guy is the reverse of this guy, right? Is the bottom keeping up with the top? No, so this just grows uncontrollably. Right? So if I do it again, what's the highest power I see? X cubed. If I do all this long ass shit here, I'll get 1 plus 8 over x cubed over 1 over x squared minus 1 over x cubed. These all go to 0. I get 1 over 0, which is the form indicating the limit is infinity. I love it. So this doesn't have a horizontal asymptote. Instead it has anybody remember the name of this? It has an asymptote. It's not horizontal though. Slant. Does it have a slant asymptote? Craziness. Okay, in fact, let me, yeah, show you this one.
Where is the slant asymptote?
I love it. Kick ass. That's exactly what I'm going to show you right now. All right. This is not his fault, by the way, what I'm about to ask you to do. This is not his fault, because I was going to ask you to do this anyway. Long divide that shit. Or, what's the better way to divide this? You guys know this? I hope to God you do. If you don't, find your pre-calc teacher, slap them. Or Or take pre-calc if you never did that. Holy shit. Right? Yeah, synthetic. I love it. Why can I use synthetic here? Because the bottom is linear. Right? I can use synthetic when the bottom's linear. I can actually use synthetic when it's not linear. It just becomes a lot more complicated. I have to do it in multiple steps. Anybody know synthetic division? As if I might bring a worksheet just in case you forgot because it's so freaking useful. So let me do long division real quick. All right, here's long division. Everybody's really excited when we do long division of polynomials. Yeah, yay. So x times what is x cubed?
Squared.
And real quick, people are always confused about this. If I had to divide this, would I divide 71? No. How would you really do that? Really think about what you're doing. What would you put up top? You could do it. Come on. It's been a while, I know, but come on. What number would you put up top? You could do it. Can you do it? I'm not going to look at 71 into 508. I'm going to look at 7 into frickin' 50. 7 goes into 50 how many times? 7. I ignored the 1. I ignored this shit, didn't I? But now when I multiply, I'm going to get 497. So that was a really good first guess, right? So that's what you really do. So look here. I'm ignoring this shit, am I not? I'm ignoring this shit. So I'm doing the exact same thing I do with numbers because variables are numbers. God damn it, right? So x times what is x cubed? X squared. So x squared times x is x cubed. And of course, when I did this, now I got to take that into account. X squared times negative 1 is negative x squared. What would I do next? What would I do with this? Change the sign. That's right. So, you're like, that's not what it is. Change the sign, because you got to subtract. Does this feel at all familiar? If you've escaped without doing long division so far, that's not a good thing. Bam. Nothing really to bring down except the 8. Let me just go and bring the 8 down. X times what is x squared? X. X squared minus x. Change of signs. X plus 8. X times what is x? 1. X minus 1. Change of sign. 9. So this is the slant asymptote. So let's take a look at what this funky ass thing looks like. Cheetahs. Where are my cheetahs? Come on. Are you alive? You'll see what I mean by cheetahs. There they are. Okay. Who am I? Alright. I want to use... Yeah, no, screw it. I'm going to use Desmos. Is that camera still going? Let's see. Yeah, he's a trooper. All right. Hasn't taken his union break yet. So if I put in here, this is so kick-ass cool. Watch this. Put in here x cubed plus 8 divided by x minus 1. Let's kind of go out a bit. There's a funky. Look at that. Now, why does it have, what's going on right here? What's this? What's going on here? See how it's going down forever and then it's going up forever? Where's the vertical asymptote? What x am I not allowed to use? I've got to put a wall there. 1. So at 1, there's 1. There is a, you're so far up there. There's a vertical asymptote up and down. So that's why it's doing that. But can you see, if I go out far enough, you start to see, what does it look like? Looks like a parabola, doesn't it? What parabola? That one. So as x gets big in both directions, it has to start to follow that. So let me put that in here. That is what a slant asymptote means. What was it? Where do you go? Plus 1. Look at that shit. That kicks so much ass. Didn't that just kind of basically go around on top of the sucker? Do you guys see that? If you had a good pre-calc teacher, you should have seen that already. Going far enough, I should be able to see Holy shit. Yeah, there you go. See, now it's starting to separate, but look, I'm like zoomed way the shit in there. All right, so when x gets really big, it's got to start to approach that blue line, and that's exactly what it's doing. That kicks ass. So asymptotes don't have to be linear. I like it. That's what a slant asymptote could be. Why was it not linear? Because these were separated by 2. I knew it was going to be a parabola. If this was a 5th power, or, let's say a 4th power, it would have been cubic asymptote. Because they would have been separated by a cube. I like it. Maybe. Okay, so let's take what we know from pre-calc, which is all this. All this is old news. This is all pre-calc stuff. And let's throw some calculus in there, which is really not that big of a step. It's not even really calculus. You could have done this back in pre-calc. But let's see what it looks like. So what about this guy? What you got, Jeff? You could do it, sure. So this is not something you'd see in pre-calc, because in pre-calc you did rational functions. Why is this not a rational function? What are rational functions? Ratios of polynomials, right? All right, is this a ratio of polynomials? I love you guys. What's a polynomial? It's got no roots, for example. Is the top a polynomial? Yes. Is the bottom polynomial? No. It's got a frickin' root, right? No. What's the definition of a polynomial? Anybody know? Give me an example of a polynomial.
4x minus 9.
I know, I love it. I was about to say, I got a special place in my heart for the person that says the one where, all right, 4x minus 9, x squared plus 2x. Somebody else was like, I was going to say that. All right, I got room in my heart. What about this? Is that a polynomial?
No.
Hell no. So the definition of a polynomial is it's a collection of terms where all variables have whole number exponents. That is a polynomial. Polynomial is supposed to have an all real numbers domain, always.